As the saying goes, when it rains, it pours. And when it pours, all sorts of debris is washed into waterways, vegetation, domestic waste of all shapes and sizes. As this material moves downstream, it can cause all sorts of damage, particularly to drainage or hydraulic structures. Often this debris can partially or fully block the structure. Naturally, these blockages can cause all sorts of problems, as it restricts infrastructure from doing its job. Increased flooding can occur, especially if the blockage occurs around the flood peak.
When you want to minimise blockage, the main means of doing that is to increase the size of the structure. Generally, the smaller the structure, the bigger the risk of blockage. So if we have a bridge instead of a culvert, for example, that will reduce that risk of debris getting stuck on the culvert. So a bridge or a large culvert can allow bigger material to flow through following the channel. Once it's a little smaller, there's a risk that a branch or other floating material will get stuck in the entrance of the culvert. Smaller material gets stuck on it and that will block. So generally it's to make the structure larger. There are some other structural measures. If you do have a culvert already there that is at risk of blockage, we can put deflectors or grates at the entrance of the culvert to collect it before it does get stuck in the culvert. The blockage considerations is really, a lot of design guidelines have information on what percentage of the culvert is assumed to be blocked. And these are generally just, in the past, have been based on what people think is a good idea without a lot of facts and figures there. And so the guidelines really have to work out how do we estimate the amount of blockage, and then what do we do when we do the hydraulic analysis of the culvert with the blockage there. And the guidelines, we need to make sure that when we set up the guidelines that we design the culverts for the expected amount of blockage so that we match the probability of the flood with the blockage to what will happen on average. So we need to have that probability worked out right. The criteria, the most important criteria, there's several of those. One is the availability of debris that can get into the river and hit the culvert. The second is how quickly can that debris move, and then what's the risk of it being caught. So they're the three criteria, and they can be very variable. So in some catchments we may have a lot of debris, but it's not likely to move, or it will be caught on structures upstream. So we need to look at all three of those criteria and use that to estimate the amount of blockage in each culvert. So the main elements of managing blockage in a structure is really, firstly, of what happens in the catchment. Where does the material come from in the catchment that's likely to cause the blockage? And that will be encouraging soil conservation to limit the amount of erosion, controlling the vegetation to limit the amount of vegetation that gets washed into the creek, controlling what material is in the creek, controlling what people have in their properties of material that's likely to float out. And this can partly be a public education to encourage the public to maintain their properties, to limit that amount of blockage. Once water's in the channel, found its way to the drainage structure, it's really then you can have design of grates on the structure to prevent material getting in, diversions to make sure that material that may block the structure is diverted away from the culvert and stops it actually getting there to block it. The main advantage of introducing new guidelines is really to improve consistency and reliability. At the moment, there seems to be many designers of drainage systems don't assume any blockage. They assume none. And that may be an extreme at one end. At the other end, some people do assume an extreme amount of blockage. And what we're really aiming to in these new guidelines is to get something that's a realistic estimate of average conditions of blockage, so that when we calculate design floods, The amount of blockage that we get is what's really represented, and our design floods represent what really happens on that watercourse.